For this next problem, we got a little setup. We got basically a couple of pulleys, and one of those ones kind of has the weight attached directly to it below there, and the other one in the middle here, we've got a little, the pulley is kind of connected in the middle of the rope instead of kind of at a frame at the side there. So the good thing about these pulleys with the rollers is that this allows us to easily figure out exactly what the tension is in those in those ropes, because the pulleys themselves, they don't affect the tension of the rope. They just turn. They allow the tension to remain consistent along all paths of the rope. So obviously there is going to be, if we're looking at the pulley in the corner there, we've got a particular weight that it's supporting. We've got this other tension here. This tension remains equal throughout here. So in order to maintain equilibrium, this pulley needs to also be exerting a reactionary force on at that point. That having been said, for solving this problem, we don't need to know what that is at this point. We know that since the weight W is going straight down, that is what the tension is in the rope is going to be. So I'm gonna denote that as T. Tension in the rope is equal to 800 newtons. So next things for next, we just need to draw a free body diagram of the pulley in the middle, basically. So essentially, we're going to kind of assume that those converge on a point. We've got our T's here. We've got our load P. And then these T's are acting at an angle, we'll call that theta, based upon this height h. So we don't know what that height is yet, but it can be determined. So what do we need to do in order to solve this? Okay, so take some sort of equilibrium. Are we worried about the horizontal equilibrium? Not really. We know that this T is the same. We know that they're both acting at the same angle, so we're not particularly worried about that. We know it's going to cancel out whatever it is. And we're not trying to solve for T, we already know it. So what exactly the horizontal component of that equilibrium is doesn't really matter all that much. What we do need to know, however, is what the vertical components are. So we can just go ahead and I really need to get better at doing my sigmas. There we go. Sigma Fy is going to be equal to 0. So basically we know what these forces are. We know what this force is. What we're trying to solve here is this angle here. But so we can go ahead and say that we can plug those in. So we know that the sum of the forces in the y direction, that's going to be, we've got T here, we've got 2T here. Let's just throw them in the same term because we might as well. So 2 times T times whatever the vertical component of T there is going to be. So the vertical component T is going to be based upon that angle there. It is actually going to be sine times your theta there. Sine theta. And then what's the other one we need to worry about? We got our minus P here. So we can throw the P over on the other side. and we can, well, what else can we do here? P is equal to 2t sine theta. So if we're trying to solve for theta, we've got P over 2t is equal to sine theta. So P over 2t, so our P here is 200 newtons divided by 2 times the 800 newtons, so 1600. Newtons, 2 times 800. Newtons cancel out. That gives us 125. So we got the sine of that angle there. That works out to be theta is equal to 7.18 degrees. So in order to find h, we're also going to need to take into account the fact that we do have that d value, the distance between the pulley and the center and either side of, and the supports on either side of it. So I'll just label that here. So basically, in order to find what h is, we're going to basically need to take the tangent of our angle there. So we know that tan of that angle is going to be equal to h over d. So tan of that's equal to 0.126. And again, that shouldn't be surprising. For small angles, our tan is usually fairly close to our sine. So 0.126 is equal to h over d. Solving for h, 0.126 times 600 millimeters gives us an h of 75.6 millimeters. There we go. So basically, what that's saying is, if we started with a rope that had a weight attached to it, 800 newtons on this pulley, if that started off as taut, and then we added another weight in the middle of that on another pulley, that's going to cause it to sag. I guess I should draw that line underneath there. That's going to cause that to sag a certain amount due to the additional force imposed, and that amount of sag is going to be around, it's going to be around 75 millimeters. That's about that.